inviting me, and thank you to Sangil for inviting me to KAIST. It's an honor to give a talk here. So the plan was to talk about a problem that is known as a hypergraph dualization, or sometimes it is called the transversal problem. So my talk will be first, I want to define what is the problem hypergraph dualization, and the links, what is an enumeration algorithm, because it's a problem that has to enumerate some sets of objects. And then I will make a link from the enumeration, from the hypergraph dualization, to a known problem in graph theory, that is the minimum dominating set, and here the enumeration of minimal dominating sets. So it's somehow surprising, because it's the minimal dominating sets is a small class of problems, and compared to the number of problems that can be defined as a hypergraph dualization. And this means, okay, maybe we can use graph theory to solve this open problem since 50 years. That has 50 years, that is old, since the 60s. So what is the links between, for instance, okay, I give you a CNF formula, a monotone CNF formula.
Maybe you have to explain for some
yes, for the, so monotone, so a CNF formula, that means just you have a disjunction of conjunction it's the similar, okay, so that's conjunction of disjunctive formula. So close this, okay, so that means x1 or x2 or x3, for instance, and oops, you want to satisfy all these clauses, okay. So because we know that all these are SAT formulas, then we say that, okay, they are equivalent to formulas of size, at least each clause is of size 3. So monotone, if you have such a formula, you say it is monotone. So this means that, okay, if you take some assignment of the variables in your formula, so you can order them with a lexicographic ordering, saying, okay, this is smaller, everything is smaller. Then it is monotone, means whenever x is smaller than y, then if you apply, this is my function f, then this means f of x bar is smaller than f of y bar. Okay, so meaning, okay, once this formula has a model, all the models above also satisfy the formula.
So f of x
is, say, okay,
like either true or false, right?
Yes, it's either true or false. That means, okay, if f of x is true, then f of y is true, okay. And if f of x is false, then maybe f of y can be true. But we know that once this is true, then everybody above is true. Okay, so these formulas are special cases of SAT formulas. Now you want, for instance, the links between, and you give me, this is 2n sets, subsets of 1n. Now you give me an anti-chain. Okay, so C is an anti-chain, for instance. Donc C, a subset, an anti-chain. Okay, so you want to compute. Donc the question, so compute the minimal of minus C. Okay, so if you look, so you take the filter of C, so you have all the sets that are below of subsets that are on C, on the C. Now you take all the sets that are not in C, and you want to compute the minimal ones. Okay, so now it's commonly known that okay, this problem and this problem are the same, they are equivalent. If you can solve this one in polynomial time, then you can solve this one in polynomial time.
By
So
solving CNF form, like you want to find.
yes, you want to find an assignment, or okay, here you are interested in okay, if I give you this formula, you want to find an assignment. The easiest way is to compute the disjunctive normal form instead of the conjunction of disjunctions. So the DNF formula. The DNF formula is of that form. Okay, you have a disjunction of conjunctive form. Okay, so checking the satisfiability of this is more or less, the computability is more or less the same as computing this formula, this equivalent formula. And you know that this you can check it easily. Its satisfiability you can check it easily. So that means okay, the satisfiability of this one and this one are similar with respect to complexity. So here what you give as input is C. Okay, now you give C, and what you have is a collection of subsets also. So what does it mean polynomial? So you need to be careful what you mean by polynomial in this way. So this problem is known, they are equivalent, and this is a problem known as hypergraph dualization. So this is a hypergraph dualization.
So, okay, I forgot. So what is the location to the end bars?
It's all the subsets. I take all the it's a Boolean algebra. So this is all the subsets that are not in C. C is a collection of subsets.
Right.
Okay, C is included in 2 to the n. And I want to compute the minimal sets that are not in the filter of C. So the filter of C is all the C prime included in, all the C prime included in C and C. Okay, so what you want is minimal sets that are not subsets of C. So it's similar to like this, to computing this there. So this problem is usually named as a hypergraph dualization. Why? Because okay, you have a hypergraph. So hypergraph is just a set V and a subset and a collection of subsets of V. That's what we call a hypergraph. Okay. Now a heating set or a transversal so a heating set is a T included in V, and such that for all E T intersects E. So this is what we call a heating set. Now the hypergraph dualization so hypergraph dualization, the question is, given a hypergraph, compute all minimal heating sets. Compute all minimal heating sets. So if you take this problem, your hypergraph is C. C is a hypergraph. So the ground set is 1 to n. So what you want is the minimal sets. Okay, if you look at the minimal sets, the border, then that are exactly those that intersect, does not intersect this. So it's like the complement, you take the complement.
Oh, you mean from the anti-chain?
Yes, from the anti-chain you take the complement, and then you want to to hit all these complements. And these are the minimal you want to compute.
Sorry, can you explain that? So
you take the hypergraph. So now for each you take it's a complement. For each set you take its complement in the ground sets.
okay.
So computing the minimal here.
Okay.
So it's just hitting these sets.
Okay. So for every member of addition,
yes, you need a complement.
And you want to have a minimum hitting set
of this complement. So, okay, this is a problem. You have your set that is given, the ground set is given. This you can solve it, it's decidable. How? Okay, you could take all the possible sets and then you are done. But this is not interesting. Because if you ask to compute such a set, then you want to compute it as fast as possible. So compute it as fast as possible, so you cannot use same notion as in classical computational complexity. Because in classical computational complexity, the set or the solution you want is usually of size similar to the size of the input. If you give me a graph and you want to say, do I have a minimum dominating set? Do I have a minimum vertex cover? Then the size is smaller of the graph, okay? So then the complexity, you can say, okay, I can express it in terms of the size of the input. But here, it's not the case, okay? The complexity, I cannot express it only in terms of the input because morally, it can be exponential in terms of the input. For instance, C can be small, but if you look at the minimal in the other size, it's big. Usually I give you a small sub problem, then if you look at the DNF formula, it's exponential. So here, the output can be exponential in terms of the input. So we need to define what does it mean computing efficiently the minimal hitting sets in a hypergraph. So what does it mean enumeration algorithms? Okay. So enumerate, so given a set C of objects, that's just a set of objects. So enumerate C is outputting, the goal is to outputting the elements in C without repetitions. So you don't want to repeat. You want an algorithm that will enumerate, that will list each object one by one, and you don't want to repeat the objects you are listing. So for instance, a gray code, you want to, if you want to enumerate all, example, enumerate all n vectors, all vectors of size n, okay? So you want to enumerate all vectors on 0, 1 of size n, so you will start from one vertex and then construct another vector and then until you get all the vectors of size n. And in this process you don't want to repeat. So each object is exactly computed once. So these are enumeration algorithms. So now the complexity given since the input can be smaller, much smaller, can be too small than the output. Okay, the efficiency is with respect to the input and output. Okay, you take into account the input and output to say what is an efficient algorithm. So in terms of hypergraph, for instance, because you can define it with, so in terms of hypergraph, so what you say, okay, you have a hypergraph H, and a property, say P of X, example, say X is a heating set. Okay, so I give you a property on the subsets of the elements of the hypergraph, the ground set of the hypergraph, and you say, okay, P of X, say X for instance is an independent set, X is a heating set, and so on. So the enumeration algorithm for P is to enumerate all subsets of P of V that satisfy P. So you want all these subsets. Now its output, we call this enumeration algorithm has a polynomial algorithm. So such an enumeration algorithm is output polynomial. Okay. Such an algorithm is output polynomial. Okay, we say that it's output polynomial if there exists a polynomial that enumerates, if there is a polynomial such that the time complexity is bounded by so this is the size of the hypergraph. Okay, the size is usually counted as the number of elements of the ground set and the sum of the sizes of all the hyper edges. So it's the usual, it's like if you give me a graph, then I will count the number of edges and the number of vertices has the size of the graph. So here we have subsets, so I need to count the size of each subset. So I will count all. Okay, so this is the sum all, and the size of this is just, okay, the size of all the set X included in V such that P of X is true. So this is also a hypergraph. Okay, and then you will say that your enumeration algorithm is output polynomial if the time complexity is bounded by such a polynomial. So this is strong in the sense that you count at the same time the size of the output and the size of the input. So now it is polynomial delay. So it is incremental. So it is incremental. If you can, if between the i's solution and the I plus 1's first solution, because when you output, you will first output 1 and then the second and then the third and so on. Okay, so if between the I solution and the I plus first solution, so the time complexity is bounded by P of H also, and the size of the I first solution. So what does it mean? That means, for instance, to compute the first solution, the time complexity is bounded by the size of the hypergraph. To compute the second solution, the time complexity is bounded by the same polynomial on the size of the hypergraph and on the size of the first solution. And then to compute the third solution, it depends on the hypergraph and on the size of the first and the second solution, and so on and so on. That means at each step, you have a way to output one by one, and the time complexity depends only on what you have already been computed. Okay, so now an incremental is polynomial delay if this polynomial does not depend on what you have already computed. So it is polynomial delay if the delay between two solutions is bounded by a polynomial. It is bounded by a polynomial on H. Now, what you will compute does not depend on what you have already computed. That means you first compute the first solution, and then in terms of the hypergraph, you can compute again the second solution. In terms of the hypergraph, you can again compute the third solution, and so on and so on. Okay, so usually when you do this, it's like, okay, you don't really need much information from what you have already done before. So what you have already output before, you need only a polynomial number of operation, a polynomial number of memory to compute the next solution. So what we have is, okay, from this you have poly delay is included or not in the incremental. That means every polynomial delay is an incremental polynomial time algorithm. Now we don't know if it is strict or not. So, but we know that every incremental polynomial time is a output polynomial, and we know that it's strict.
How do you know that it's strict?
Well, you can prove that if they are equal, P is equal NP.
Okay,
assuming P is different from NP under the time complexity conjunction, then you can prove this. There are some reductions that, okay. Of course, you can have something more efficient than polynomial, say linear delay. Linear delay means the polynomial is a linear function. You can have a constant delay. Constant delay, the polynomial is a constant. For instance, if you want to enumerate all vectors of size n, then there is a constant delay. That is called a gray code. You can enumerate one by one, and at each step, the difference between the solution before and the next solution is just you flip one bit. And then you can enumerate all vectors with constant delay because you just flip one bit at each step. Questions? So the hypergraph dualization is only, at this point we even don't know if there is an output poly algorithm. So what is known, the best known algorithm for hypergraph dualization is by Friedman and Kashian. There are also variants. in 96 is so the complexity n is the size of the input and output. Okay, so n size of input plus output. Okay, so this is little o. It is the best algorithm we have. So it's not incremental, it's not output polynomial, it's just quasi-polynomial. But there are classes of graphs, of hypergraphs, where people know efficient algorithm.
So is n the number of input? I mean, it's the size of the
size of the input. It is the size of the, size plus the size of the output. So tractable cases, examples of tractable cases. Okay, so beta acyclic hypergraphs. Beta acyclic means, okay, it's a notion of acyclicity in hypergraph. There is a way, okay, to remove one by one the vertices and the edges of your hypergraph until you reach the empty set. And the rule is simple. If the vertex is in one, then you can remove it. And if a hyper edge is included in another one, then you can remove it. And if you do that, then you have an alpha acyclicity notion, and a beta acyclic, that means the graph has such an ordering, and every induced every subhypergraph has also this ordering. Because if you take a hypergraph and you add all the one hyper edge, that is the ground set, then you are alpha acyclic. So the alpha acyclicity is not closed under induced subhypergraph. Even induced in the under.
Induced, you mean you take a subset?
Yes, you take a subset of by subhypergraph. I mean, sorry, you take a subset of the hyper edges. Then you are not alpha. You may be not alpha acyclic. But beta acyclic, that means if I am alpha acyclic and every subhypergraph is also alpha acyclic. If I take any subset of the hyper edges, then I have also such an ordering. That where I can remove one by one the elements until reaching the empty set. So another one.
So for the beta acyclic hypergraphs, the hyperdualization is
yes, and it is even polynomial delay. You have a polynomial delay, a polydelay algorithm. So you have, for instance, bounded Trewitz hypergraphs. So hypergraphs have bounded Trewitz if the incidence graph you associate with it has bounded Trewitz. So if you take the more general notion of Trewitz, hyper-Trewitz, generalized Trewitz, this is false. So you can prove that it's similar to the general case. It's already proved. So bounded degeneracy. So degeneracy means, okay, you can enumerate, you can list the vertices in such a way that at each step, if you look at a vertex, it is in a bounded number of hyper edges. So this generalizes the genericity in graphs. And the bounded conformality. So this is polydelay. This is incremental. So these are more or less the most general classes of hypergraphs where we have an output polynomial algorithm. After you have some subclasses like for interval hypergraphs, some geometric hypergraphs where you have output polynomial or not. But these are more or less the more general cases that are known. So if you know what is the Helly property, yes, the conformality is if you take a hypergraph, you take its dual. Okay, it is a hypergraph is K conformal if and only if its dual is K Helly.
What is K Helly?
K Helly, if you take any K subsets of hypergraphs that have then all of them have intersection. Any K subsets has, then all have. So now in the dominating set problem. So the hypergraph dualization is a special case of a more general problem of enumeration algorithm, and this more general problem is known as a dualization problem, and this dualization problem is in general NP complete or co-NP complete. It depends how we define it. So the quasi-polynomial algorithm says that more or less it's a conjecture that it cannot be co-NP complete, the hypergraph dualization, because it is in NP intersection co-NP, and it has a quasi-polynomial algorithm, so it cannot be co-NP under some assumptions. So now the dominating set problem, the enumeration of minimal dominating set. So graph G, graph D included in V is a dominating set if so this is neighbors of V including V. Okay, you take the close neighborhood of V, that means you take all the neighbors of V and you add V. Now if you take D, you say it's a dominating set if it intersects this set. So that means every vertex is either in D or has a neighbor in D. That's what is a dominating set. So we want to enumerate the minimal ones. Still with respect to inclusion, okay, saying okay, this one is not included in the other one. So special case of hypergraph dualization. Take this hypergraph If you take this hypergraph, then you are a dominating set if you are a hitting set. So if you want to enumerate the minimal dominating set of your graph, it's similar to say you want to enumerate all the minimal hitting set of this hypergraph. Okay? So reduction is polynomial in the sense that from the graph in polynomial time, with respect to the graph, you can construct this hypergraph. Okay? So there is something that, okay, there exists hypergraphs H such that H is different. This is known. So any hypergraph, it's not true that any hypergraph is a neighborhood of some hypergraph, of some graph. So this is a well-known result. And now, okay, that this may say the hypergraph dualization is much harder than the enumeration of minimal dominating set. For several reasons. First, there are many special cases of the hypergraph dualization in graphs that are easy. You want to enumerate the clicks, the maximal clicks. So you hit every edge. You want to enumerate the maximal independent sets. So you hit non-edges. You want to enumerate the spanning trees. You hit the circuits, the cycles. You want to hit the basis of a metroid. So you hit the circuits of the metroid, and so on and so on. So many cases in graphs are special cases of the hypergraphs, and for many of these, then you know a polynomial time algorithm. You can enumerate the multipartite, complete r-partite hypergraphs, and so on and so on. So that would suggest that, okay, the minimal dominating set is a special case. But unfortunately, you are surprised that this is not the case. The minimal dominating set is similar exactly to the enumeration of minimal hitting sets in a hypergraph, and this in a strong way, in a sense that you have a polynomial delay for the minimal hypergraph only if you have a polynomial delay for the minimal dominating set enumeration. So
why is it unfortunate?
Well, we were hoping that, okay, it's smaller and then it's easy. And it's not easy because, well, we will see after. And I hope that we will have time to show at least 2 examples. So I will show you the reduction quickly, okay? So if I give you a hypergraph H, say I will have E1, E2, EP, and I will have V1, Vn. So I will construct the incidence hypergraph. The incidence graph of this hypergraph is that, okay, it's just the graph. Has vertices the ground set of your hypergraph and has other vertices the hyper edge of your graph, okay? And you add an edge between a vertex and a hyper edge in the graph if the vertex is inside the hyper edge, okay? So now what you do, you add a new vertex and you turn this into a click. You turn this into a click. Okay, you have 2 clicks, and what you have here is a co-bipartite graph. Now you can prove that, okay, a transversal.
Hitting set, right?
Yes, a hitting set. A hitting set of H is a dominating set. So this is called B of H. Is a dominating set of B of H. So that means if you have a minimal transversal here, you will have a minimal dominating set because of this lemma 2. So a dominating set, a minimal dominating set in B of H has size at either 2 or is a minimal hitting set of H. If you take any minimal dominating set of this graph, so assume it should intersect this part, okay, because V does not see anything here. So if it intersects this part, so you take 1, it dominates everything here, okay. Now if it intersects this part, then again you take 1, it dominates everything here. So the size, since it is minimal, the size is at most 2. Now you take something that does not hit this part, okay, that does not intersect this part. That means it should not include V, because you should dominate these vertices, so it is included in the vertices here. Since it is minimal, then it is a transversal. Since it is a dominating set, it is a transversal. From this, you can say that it is a minimal transversal. So what does it say? That says, okay, if you can enumerate all the minimal dominating sets here, except a polynomial number, then you have all the minimal transversals you have here. And then you can enumerate if you can enumerate in output with polynomial delay, you can enumerate with polynomial delay all the minimal transversal. So because this is polynomial, number of size 2 is polynomial. It's n times m. It's n times p. It's n times p at most. So, okay, even if you restrict to co-bipartite graph, you cannot do better than hypergraph. So this means if you are weakly chordal, you cannot do better than hypergraph. If you are claw free, you cannot do better than hypergraph, and so on. So this restricts a lot the graph classes where you can look if you are interested in not solving the problem now. So okay, it's old, it's difficult. So let us try to see in which graph classes at least we can expect some small new algorithm, or at least a simple algorithm for solving this problem. The case, if you look at bounded width graphs, or bounded rank widths, bounded click widths, bounded tree widths, Kurzweil has proved that if you have a polynomial, if you have the term, if you give me the decomposition, and you give me a formula, then in linear delay, I can enumerate all the solutions. So you give me the formula, you give me the decomposition, I can enumerate all the solutions. A minimal dominating set, you can express it in monadic second order formula. Its dominating set says, okay, every other vertex either is in D or has a neighbor in D. This is a first order. Now you should say that it is minimal. So you add that every subset is not a dominating set. So then it's a monadic second order formula, and then if you have bounded widths, you can enumerate in an efficient way.
Do you care about the time to take to generate the first output?
It's linear. It's also linear. Yes, you count it in the delay. If you are interested in delay, then the time to pre-compute the first solution, then it is counted in the delay. And even here, it's linear. Well, it's a polynomial for bounded rank widths, and then for bounded tree widths, it's linear. So the algorithm is, I give you the decomposition, I give you the formula. So the formula, you can transform it into an automata. Now the term, I can transform it into something that is logarithmic, that has logarithmic height. And then after I do a product of the two, of the automata and of the decomposition. The reduction is nice because what it shows that, okay, I have a set of objects I want to enumerate, and I do some kind of parsimonious reductions, meaning I prove that there is a bijection between those objects I want to enumerate and some sets of objects I can enumerate. So in this case, what is an object you want to enumerate? It's a positive run in your automata. So what you want is to enumerate all positive runs in your automata. And positive runs in your automata are what? Are trees. So it's a kind of trees you want to enumerate in this case. So now for the split graphs. So the extension problem. So given x and y, x not intersecting y. So does there exist a mean dom? Does there exist a mean dominating set D and not intersecting y and including D, including x? So you want something such that it contains x and does not intersect D and does not intersect y. So this is the extension problem. So if this is polynomial, then you can enumerate in output with polynomial delay your solution. So what you can prove is that, okay, if the proposition is, okay, if there exists an ordering x1 xn of v such that for all partition xy you can decide in polytime the extension problem, then you have a polydelay algorithm. Okay, so if you can answer this question, if you give me an ordering and you follow this ordering, and at each step, if I give you a partition of the first I vertices, and you can say in polytime if you can extend or not, then you can enumerate in polydelay. Why? Okay, you start from the empty set and you look at is there a minimal dominating set containing x1? Yes or no? If yes, you continue. If there is a polynomial, if there is a minimal dominating set containing that does not containing x1, yes or no? If yes, you continue. If not, you cut. Okay. So assume it says yes. Now you look at x2. Is there a minimal dominating set containing x1 and x2? Yes or no? Then you continue. Is there a minimal dominating set containing x1 and not containing x2? Then yes or no? Yes, you continue. No, you continue, and so on. At each step, you have a tree. You have a path. Now when you hit the last one, xn, then you have a minimal dominating set. And the dominating set are the vertices that you have chosen to include, and the others are outside. This is, since you can ask in polynomial time, then and the tree has height at most n, then the delay is at most poly n. Okay, is n times the time to reduce this. Unfortunately, this problem is usually NP complete. This asking such, even in split graphs, if I give you a split graph and I give you x and y, asking this question is NP complete. But you can maybe try to find such an ordering usually or in a subset. So why in split graph it is easy? So in the case of split graphs, okay.
So you mean the extension problem itself is NP complete?
Yes.
The finding ordering.
You sometimes given some orderings, easy ordering, it's NP complete. In itself, it's NP complete, even in split graphs. And sometimes there are some orderings where it is still NP complete. There are some orderings that are given for some cases where it is proven to be NP complete. If you give me, we have an example, for instance, for the chordal graphs where a simple case is still NP complete. Now, in the case of split graphs, minimal dominating sets are characterized by their intersection with a click. If you take a split graph, so yes, so if you take a split graph, so okay, you can partition V into a click and an independent set. And now all the other edges are between the independent set and the click. So you have a click, you have an independent set, and you have some edges in between the independent set and the click. So you will assume that the click is maximal. Okay, that means everyone here, if it sees everyone in the click, then it will get down in the click. Okay, so you have such a thing. Now if you take a minimal dominating set, you look at its intersection with the click, then it exactly characterizes the minimal dominating set. Why? If you give me something here, A, now you look its neighbors in I. Okay, A dominates C. Now you look all its neighbors in I. Okay, so you have something like that. You have A, you have n of A intersecting I, and this is the complement. If you take A, if everyone in A is adjacent to 1, and there is one such that it is exactly adjacent to only this one vertex, and you put this one, then you have a minimal dominating set. And if you take any subset of A, then again you can define another minimal dominating set. So, okay, so what does it mean? That means if you take this set, so y is private to X with respect to D if n of y inter D is equal to X. Okay, if you take the neighbor of y in D, it's exactly X. So in split graphs, dominating sets are in bijections minimal dominating sets if you take all the subsets in C, such that if you take any element in this subset A, it has a private neighbor with respect to A, okay? If you take this set, then this is exactly in correspondence one-to-one with the minimal dominating sets. These sets, we can enumerate them easily. How? Well, start from the independent set. It's a minimal dominating set. A maximal independent set is always a minimal dominating set because everyone outside has a neighbor inside and you cannot remove one vertex. Okay? So now you start from this and then you try to add one vertex. You add one vertex, it has a private neighbor, then you can continue. You add two vertices, each one has a private neighbor, then you continue until you cannot, then you stop. And this is this problem. This is the extension problem, but X and Y are restricted on C. X and Y are restricted on C. X is always the set you have chosen. Each one has a private neighbor, and Y is a complement in C. And this characterizes your minimal dominating sets. So you have the split graph, an easy algorithm for enumerating with linear delay and polynomial space. If you want to extend this, then you can maybe define how time I remain. What time do I have?
5 minutes.
5 minutes?
Yeah.
So you can maybe extend. So take a graph G. You take a graph G, for instance. You partition the set of vertices into two sets. Okay. So you partition into irredundant vertices. And redundant. Donc redundant, you contain your neighboring, and there exists y such that n of y is included in n of x. Okay. So what does it mean? You have a vertex y that is included, such that your neighboring contains its neighbor. That means just if you want to hit this, you should hit this. That means it is enough to hit this to get a minimal dominating set. That means this is no needed in some sense. So what does it mean in graph theory? In graph theory, that means take all the redundant vertices and transform it into a clique. Okay, so transform redundant vertices into a clique. What you have is that the graph you obtain now has the same minimal dominating sets as the graph before. Mm-hmm. Now, if you start, for instance, from a P6 free chordal graphs, you obtain a split graph. You obtain a split graph. If you give me a P6 free chordal graph, you do this operation, then you get a split graph, and then in P6 free chordal graph, you can get a simple algorithm by using the algorithm for split graphs. And in fact, if you take any graph, if you apply this operation, you have at the end a chordal graph if and only if you have a split graph. Chordal means you don't have more than C3. You can have triangles, but you cannot have a cycle of length at least 4. So this is a way to say I transform a graph class into another graph class and could be able still to compute the minimal dominating sets. So you can, for instance, if you use the modular decomposition, you can also say modular decomposition, meaning you take M, you take V minus M. Everyone here either sees M or does not see all of M. So this is called a module. Then you can subdivide your graph into subgraphs, and where you don't have no module. So these graphs are called the prime graphs. So you can prove that, okay, if you want to enumerate in a graph class, it is enough to enumerate the minimal dominating sets in the prime graphs. So you have such kind of reductions that you don't have with hypergraphs, and maybe can help to solve this hypergraph dualization problem. And still don't, so you maybe we can say, let us try to understand the graph classes with respect to the problem minimal dominating sets, and then try to solve the problem. For instance, that's what we have done with chordal graphs. We use the fact that we have a click tree, and we modify the notion of extension problem in a similar way as for the split graphs, and then we were able to give a polynomial delay algorithm for this graph class. If you give me a line graph, then you can still use the structure of the line graph to get a polynomial delay to enumerate minimal dominating sets. So that means, for instance, if you want to enumerate the edge dominating sets, you can do it with polynomial delay in all graphs, and so on. I think time is gone.
Right. Thank you.